Good morning. In the previous video, we discussed about the inverting and non-inverting amplifiers using an op-amp. In this video, we will discuss another application of operational amplifier, that is, it can be used as a summing amplifier. This summing amplifier can be modified to make some other mathematical operations like subtraction, averaging, etc. That we will just briefly mention how we can modify a summing amplifier into a subtractor or an averaging amplifier, etc. So summing amplifier is actually accepts two or more inputs because we need to add something. We have more than two inputs. So a summing amplifier actually accepts two or more inputs. The output voltage of a summing amplifier is proportional to the negative of the algebraic sum of its input voltages. The negative sign actually comes from the fact that it is used in the inverting mode, or it is working as an inverting amplifier. That's why this negative sign comes. And the algebraic sum of is proportional to, if we make the gain of this inverting amplifier as unity, then we can see that the output voltage is exactly equal to the algebraic sum of input voltages. If the gain is greater than unity, then we will have the output voltage which is proportional to the algebraic sum of the input voltages. So while defining a summing amplifier, the most common statement we can use is this one: the output voltage of the summing amplifier is proportional to the negative of the algebraic sum of its input voltages. Now if we make the gain of this operational amplifier is equal to unity, then we can have exact summing amplifier. So this circuit of a summing amplifier with three inputs is shown here. You can see that here we are using an op-amp. Suppose for practical purposes we will use IC741. Anyway, it is a operational amplifier, and the two supply voltages plus V and minus V are shown here, and the non-inverting terminal, that is the positive terminal represented by plus, is grounded. So and the inverting terminal, we are applying the input voltages V1, V2 and V3 through the resistances R1, R2, R3 respectively, so that the input voltage is applied to the inverting input terminal, so it will act as an inverting amplifier. So in the case of a summing amplifier, the input is applied to the inverting input terminal. Now you can see there is a feedback resistance RF which is connected from the output terminal to the inverting input terminal, which provides the negative feedback. So this is a circuit of an inverting amplifier with negative feedback having more than one input voltages. Now let's see how this output voltage is proportional to the algebraic sum of negative of the algebraic sum of the input voltages. So we have to show this V out, the output voltage is proportional to the negative of the algebraic sum of the input voltages. So typically consider, here we are having three input voltages V1, V2 and V3. They are connected to the inverting input terminal through the resistances R1, R2 and R3. Here you can see that the current I1 is the current flowing through the resistance R1 and I2 be the current flowing through R2 and I3 be the current flowing through R3. That means the resistance R1 draws a current I1 from the voltage source or input signal V1 and R2 draws a current I2 from the voltage source V2 and R3 draws a current I3 from the input voltage source V3. Now they are combined or connected to the terminal A or the node A, which is actually at a virtual ground. So by considering the infinite input impedance and virtual ground concept, we can say that there is no current flowing into the operational amplifier, so that the current, sum of the currents I1, I2 and I3 which reaching the node A continues their journey to the feedback resistance RF, or we can say that which is equal to the current flowing through the feedback resistance, which is denoted by IF. So I1 plus I2 plus I3 is equal to IF when we consider the node A according to the Kirchhoff's current law, and the current flowing into this operational amplifier is equal to 0 because of the infinite input impedance and virtual ground concept. So now let's rewrite this current equation in terms of the voltages. Here I1 is equal to the current flowing through R1. So current flow, the direction of the current flow is represented from here to here, so that we can call this as the higher potential and this as the lower potential. Actually this end of the R1 is connected to the node A, so it actually represents the voltage at the node A, and this represents the voltage, and the voltage at this node is V1. So the voltage I1 is the current flowing through R1, which is equal to voltage across R1 divided by the resistance R1, which is equal to the voltage across R1 is V1 minus VA divided by R1, but according to the virtual ground concept, VA is equal to 0. The voltage at the node A is 0 because this node is equal to 0, so which is equal to V1 by R1. Similarly, we can write the expression for I2 as I2 is equal to V2 minus VA divided by R2, so which is equal to V2 by R2, and also the current I3 is given by I3 is equal to V3 divided by R3. Similarly, the current IF can be written as IF is equal to the voltage across RF divided by RF, which is given by, here the current, direction of the current is represented from here to here. That means we have to consider the potential at this point VA and the potential at this point is actually the output voltage, so V0. So current, here it is VA and here it is V0. The current is flowing from VA to V0. So the IF can be, expression for IF can be written as VA minus V out divided by RF, but VA is equal to 0, so IF will be minus V out divided by RF. Now if we substitute the values of I1, I2, I3 and IF in the expression for the current in the circuit, or in this expression I1 plus I2 plus I3 is equal to IF, we will get V1 by R1 plus V2 by R2 plus V3 by R3 is equal to minus V out by RF. Now if you make these three resistances R1, R2, R3 are equal, let us say they are equal to R, then what we will get is that V out, I am rewriting this equation like this, V out by RF is equal to minus 1 by R into V1 plus V2 plus V3. So V out is equal to minus RF by R1, minus RF by R into V1 plus V2 plus V3. For a particular circuit, this RF by R is a constant, so this V out is proportional to negative of the sum of the input voltages. So this circuit shown here is actually represents the, or gives a voltage, output voltage, which is proportional to the negative of the algebraic sum of the input voltages, which is the action of a summing amplifier. So this circuit works as a summing amplifier. Now if we make this ratio RF by R is equal to unity, just by putting RF is equal to R, then we will get V out is equal to minus V1 plus V2 plus V3, so it represents a summing amplifier. Now suppose instead of this one, if we make this ratio, suppose if we are having 3 input voltages, if we make this RF by R is equal to 3, or RF is equal to 3R, there is no negative sign, so RF equal to 3R, that means if you take R is equal to 1 kilo ohm, then RF will be, if you take it as 3 kilo ohm, the output voltage will be equal to minus 1 by 3 into V1 plus V2 plus V3, which actually gives the output voltage equal to the average of the input voltages, sum of the input voltages, so which is called an averaging amplifier. Or it is an averaging circuit. So to find the mathematical action of averaging, we can use an operational amplifier with a condition that the input resistances are made equal, and there will be, and the feedback resistance should be the number of feedback resistance should be equal to the resistance multiplied by the number of inputs. So that will serve as a averaging circuit. Now we will, instead of it, suppose we are considering a circuit like this. Suppose we are having an op-amp. I am considering another circuit like this. The supply voltages are provided here. The non-inverting terminal is grounded, and I have two input voltages. One input voltage I am giving here, the non-inverting terminal, so let it be R. Then here I am giving the voltage V1, and the feedback resistance is also R, that is equal to the input resistance is given here. Then the output voltage at this end will be P out is equal to minus R, actually RF by R I into V in. Here the RF and R are equal, so minus R by R is into V in, so which is equal to minus V in. So the output voltage at this node will be V out is equal to minus V in. Now I have another op-amp. The second op-amp, supply voltages are provided here, and this voltage is given to the non-inverting terminal, inverting terminal. The non-inverting terminal is grounded, and the second voltage source V2 is connected to the resistance through the resistor, same as the previous one R, and I am using a feedback resistance here. It is also R. So for the second op-amp we have two input voltages. One is V2, and here it is minus V in, means minus V1, that is the V in is actually minus V1, so minus V1. So it has two input voltages V2 and minus V1, and the output voltage will be, here also I am using a resistance R to connect to the terminal 2. Then the output voltage will be equal to R by R, so it is minus, these two resistances are equal, so it can be used as minus the feedback resistance divided by the common resistance into V2 minus V1. Here it is actually V2 plus V1, but V1 is negative. One of the input voltage is minus V1, so it will be minus of V2 minus V1, or V1 minus V2. So V out will be equal to V1 minus V2. That means if you have two input voltages V1 and V2 and they are connected in this way, then we will get the output voltage which is equal to the difference of the two voltages. So here it will act as a difference amplifier. So it is called a subtractor. So the summing amplifier can be modified as a subtractor also. That is another advantage of or application of a summing amplifier. So this is about the summing amplifier. And now two more important application of operational amplifier is that it can use to perform the mathematical operations like integration and differentiation, that we will discuss in the next video. Thank you.